Okay, so the second part of simple harmonic motion is talking about damped simple harmonic motion. So what we're looking at is damping being applied to simple harmonic motion. So what happens is the amplitude of each oscillation will decrease because damping just means to reduce that amplitude. So the concept's very important, and we see some applications around us. So I have 3 examples of types of dampening. Some of them types of damping. Some of them you're going to see, and one you're not, and we'll explain the why here. So, over damping. First one here, oscillation ceases and the mass slowly returns to its equilibrium position. So on the graph over here, if we put delta x and over time, so we're looking at how does the sway occur over time, or how does it reduce. What's happening is that we get a nice smooth curve, and it returns down to no oscillation right away. So some of the examples here, car shocks. If you're riding in a car, it brings you back to that equilibrium position after going over a bump virtually immediately, okay? Where you can also do the cylinders on screen doors. Cylinders on screen doors. So if you have a cylinder tied to your door, one that doesn't allow it to close very, very quickly. So if you try to slam a screen door, it won't work because that cylinder stops it. It does a nice smooth curve and brings it back to that rest position. Also, you might have on cabinetry, so kitchen cupboards, kitchen cabinet door, and I think they're called stops, where basically you can't slam a cabinet door. So if you go to get a glass out of the cabinet to have a drink of water, you close the door, it automatically closes. Well, that's what it's doing. It's bringing it back to the rest position in that nice smooth curve, returning it like that. So it doesn't slam, but it returns to the closed position. So that's what we call over damping. It returns in one motion back to a closed position. Critical damping. This is where the oscillation will cease and the mass moves to equilibrium as fast as possible. And this is a theoretical situation, so you're not going to see this in nature. What this will look like, delta x, delta t. So this is what those manufacturers are really looking for, and they're looking for something that will return it in an optimal amount of time. So it gets a curve that kind of looks like that, where it slowly moves it, closes it quickly, and then slows it down so it doesn't bump or slam there. So this is what they shoot for, but you're never going to see this. There's no real-world application at this point in time anyway. So no real-world application. All right, and the last one I want to look at here is what we call underdamping. So when does underdamping happen, or what's it look like, first of all? So if you stretch it out or open something, what happens is you get this type of motion. It kind of swings back and forth until it reaches that closed position. So I always get, students always tell me saloon doors. Everyone that watches a Western, or if you go to our office, in the main office there, they kind of have the saloon doors where you walk back to where the secretaries are working. Those doors will flip-flop back and forth, slowly oscillating to the point where the amplitude's 0 and they remain closed. Okay, a little bit annoying when you're following behind. Another good example is Newton's cradle. And that is the set of balls that click back and forth. Okay, so a little tough for me to draw here. If you just Google it, basically what happens is you pull that ball back, swings, and the one that on the end will then swing out, and then will return, and you get the click, clack, moving back and forth. So you just Google that and you get a good example of that. And the other one's kind of neat, goes with my background in engineering, skyscrapers. Skyscrapers. All right, and as an example, I'm going to show you in the next slide here, in the next part of the note, how they work in terms of the underdamping. So, engineering application for damped simple harmonic motion. Oh, skyscrapers. I always like those skyscrapers. Let's get rid of a P here. Oops. So skyscrapers and oscillation. So let's take a look at what happens in an earthquake. So if you have a typical office building, high rise, that's going to be the equilibrium line. That's that's the true line that you want a building to stay around. What happens with the earthquake? Earthquake shakes the ground back and forth. All right, that's what an earthquake does. It vibrates the bottom. So what happens is you move the bottom of the building, the top has to follow along. So initially then, my skyscraper is going to bend in one direction. Obviously this is not to scale and it's exaggerated for note purposes. Here's the equilibrium line. Here's that center of mass line. So that means the top of my building has moved or shifted delta x from that from the center line, from the line where it's standing straight up and down. Stage 3, the building will return to that center line. However, the top of this building now has a velocity because this wants to right itself. The only way it can right itself is by moving back. Well, buildings don't have the ability to come to a stop. They don't have brakes. So that means that building's going to continue on its way. And that's what my stage 4 drawing is. And oops, that draws stage 4 drawing properly. So now, again, I'm exaggerating for note purposes here. It's now flexed this direction. And the big concern with earthquakes, put my center line in again. Here's the center of the building line. As a building oscillates in an earthquake, and the reason we end up with failure is because this is growing. That distance is actually growing. So we end up with the original deflection, delta x, plus a little bit more, delta y. So that actually the building, once it starts flipping back or moving back and forth, it actually magnifies itself and it's going the wrong direction. It's not damping, it's actually, we got constructive harmonic motion going, which means it's getting greater and greater. And that's because that center of mass, okay, we're getting further and further over. So if I ask you to bend over at the waist, you can feel that tendency to fall out of your chair or fall forward. Okay, just be careful before you try it. But what's happening then, as that weight increases, that flipping back and forth, that's what causes the buildings to fall in an earthquake. So how do we fix that? Well, I'm going to show you the simple system. There's a bunch of systems out there and they've changed it, but originally, this one's easiest to explain. What they did is they put a U-shaped water tank on top, filled it partially full of water. All right, so the earthquake occurs. Now Newton's first law says whatever is not in motion wants to stay in that current state. So when this building then rotates or bends, so I'm going to try to draw it similar to the one above. Here's my center line. Here's the center line of the building. There's my delta x. So there's delta x. We take a look at that water tank that's built. Draw it somewhat to scale. What happens is the water doesn't want to move. The water wants to stay stationary. So what happens, because all that water rushes to the one side, this tank will fill up because it doesn't want to move. So you end up with a water distribution like that. Maybe we'll even exaggerate a little bit more. All right. So it rushes all to one side. So what it does is it moves more water stays in the middle, kind of in this safe zone. And it means that that center of mass is actually more in the, or there's more mass in the middle. So then we get stage 3, where that building returns back to the equilibrium position. Water returns back to its happy state in the middle here. We have a velocity this direction, but if I put above VU for undamped versus VD, we see that the velocity of the top of the building is much less than the velocity of the undamped. And that's because there was less deflection because of that mass staying more in the middle. So when we go to stage 3, and I'm going to oversimplify this, so for people that are watching this with engineering degrees, keep that in mind that it's an introduction to the topic, so don't be writing in saying I'm not completely being accurate. I know that already. So as it flips onto this side, it's actually going to be its deflection, because all that water now rushes to this side of the tank. That deflection, keeping it simple as to saying it's actually going to be the original delta x, but now it's going to be subtracting delta y. That's because there is less sway. So that water tank on top, hey, now is reducing the amount of sway because it's keeping the majority of the mass in that safe zone, in that center structure. So that damping effect. Now, they don't put the water tanks, originally they put the water tanks up there because it gave the building more pressure, so they pump it up there. They've come up with better systems now, a little bit more efficient, as those large water tanks aren't needed as much anymore, but it gives you a general idea of what to expect. All right, so that's how it works in a very simplistic format. So it just keeps that center of mass over the middle and reduces that sway. We get less sway. So we're actually taking away displacement rather than adding to it. So damped simple harmonic motion equations, they're very complicated. So they require some second-year university calculus to solve in a lot of cases. So for our purpose, we're going to simplify the situation by choosing an equation that it closely models the scenario. So if you go in and do some kind of engineering where you're looking at earthquake analysis, the equations are going to be a little bit more complicated. In grade 11 math, so what we're going to use, you talked about two different types of growth. So we're just going to go back to good old grade 11 for a second. That was your exponential. So here we had growth. And this one, the other that you talked about was decay with the exponential. So we're interested in the second type of exponential function. All right, we're interested in decay because we're looking at damping something, so we're reducing that magnitude every time. So we're talking about elastic energy. It's going to equal, and I am going to put a physical box here, so it's an empty box, E. We're going to talk about that for those that are taking calculus in vectors. The E function, we'll talk about that. That's just a number. I'll put that off to the side in 1 second. B T over M. So here, where E is approximately equal to 2.71, and we ask about that in class a little bit. B is a constant for the structure, so it depends on the building. All right. M is the mass, and T is how much time the oscillation has occurred. All right, and this in here is a simple harmonic equation, and this is where sometimes you get into some complicated university math. And like I said, I'm going to simplify for any of the examples or homework we're going to do, just so that it's something, gives you a taste of what to expect, but not the exact things. So I believe we got one more example. I'm going to, rather than rush through, I'm going to do it in the next video, and then we're all set to finish up this unit.